A few years ago, researchers watched an octopus do something that shouldn't make sense. It picked up two halves of a coconut shell from the sea floor, carried them awkwardly across open sand, then assembled them into a shelter when danger approached. That's tool use, planning for the future, problem solving with objects that serve no immediate purpose. This animal has no bones, no society, and a brain smaller than a walnut. Yet it just demonstrated foresight, a cognitive ability we used to think belonged exclusively to humans and a handful of other species. What you're looking at isn't just clever behaviour, it's intelligence that evolved completely independent of our own, following rules we're only beginning to understand. Octopuses aren't mammals. They're not even vertebrates. They're mollusks, sharing a family tree with clams and snails. Somewhere around 600 million years ago, our ancestors and theirs split paths. Everything that happened after, every adaptation, every evolutionary pressure unfolded separately. And somehow, against every prediction, both lineages arrived at intelligence. But the octopus version looks nothing like ours. Start with the nervous system, because that's where things get strange. Humans centralize control. One brain sends commands through the spinal cord to the rest of the body. Top down, hierarchical. The octopus does the opposite. It has roughly 500 million neurons, comparable to a dog, but 2/3 of them exist outside the brain, distributed across 8 arms. Each arm operates semi-independently, processing sensory input and making decisions without waiting for approval from headquarters. Cut off an octopus arm and it keeps moving. It explores, it recoils from unpleasant textures. It behaves like it still has a mind because, in a very real sense, it does. The arm contains enough neural tissue to function autonomously, at least temporarily. This isn't the brain delegating tasks. This is genuine decentralization, a fundamentally different architecture for organizing thought. Why build a nervous system this way? Consider how octopuses hunt. They squeeze into crevices, probe under rocks, reach into spaces their eyes can't see. Routing every piece of sensory data back to a central processor would create delays, so the arms handle tactical decisions locally while the brain manages strategy, navigation, and memory. It's delegation at a biological level. And those arms aren't just touching things, they're tasting them. Every sucker is packed with chemoreceptors. When an octopus wraps around an object, it's simultaneously feeling texture and sampling chemical composition. Imagine running your hand along a surface and instantly knowing what it's made of, whether it's edible, whether it's been touched by predators. That's the octopus experience. With every movement, their eyes tell another story. Camera-type lenses, just like ours, iris, retina, focusing mechanism. It's one of evolution's most striking examples of convergent design. Two completely unrelated lineages solving the same problem with nearly identical solutions. But there's a critical difference. Vertebrate eyes have a structural flaw. Our optic nerve punches through the retina, creating a blind spot where photoreceptors can't exist. It's evolutionary baggage, a consequence of how our eyes developed. Octopus eyes avoided this mistake entirely. Their photoreceptors face the light and neural wiring attaches from behind. No blind spot. Seamless vision. If you were designing an eye from scratch, you'd build it like an octopus. They also detect polarized light, the directional oscillation of light waves. It's a dimension of vision humans can't perceive. This lets them see transparent prey like jellyfish, pick out contrast in murky water, possibly even communicate through skin patterns invisible to most predators. Their visual world contains information ours simply doesn't include. Which makes the next part genuinely baffling. Despite all this visual sophistication, octopuses appear to be colorblind. They have only one type of photoreceptor for color detection. So how does an animal that can't see color match its surroundings with such precision that it becomes functionally invisible? The answer might be that their skin sees for them. Researchers found light-sensitive proteins called opsins distributed throughout octopus skin, the same molecules that detect light in their retinas. Their skin may respond to color directly, bypassing the brain entirely. They don't need to look at what they're camouflaging against. Their body senses it and adjusts automatically. Think about what that means. Perception without awareness, response without conscious decision. Intelligence distributed so thoroughly that the boundary between sensing and thinking becomes unclear. And camouflage itself operates through principles we're still mapping. Octopuses don't change color like chameleons, which restructure nanocrystals over several seconds. They use muscular chromatophores, elastic sacs filled with pigments surrounded by radial muscles. Contract the muscles, the sac expands, color appears. Relax them, it vanishes. The whole system operates in milliseconds, faster than most predators can track. Layered beneath are iridophores generating metallic blues and greens, then leucophores scattering white light. But color alone doesn't sell the illusion. Underneath runs a network of muscles called papillae that raise skin into three-dimensional textures: spikes, ridges, branching structures. The octopus doesn't just match color, it sculpts itself into coral, rock, algae. Which raises an uncomfortable question. When an octopus transforms itself to blend with a reef, is it making conscious choices about pattern and texture? Or is this reflexive sensory input triggering automatic responses throughout a distributed nervous system? The evidence points towards something between pure reflex and deliberate control. Octopuses learn to produce specific patterns through training, suggesting voluntary command. Yet the speed and complexity imply significant automatic processing. What we're witnessing might be high-level decisions about which general strategy to deploy, with low-level execution handled by semi-autonomous neural networks. We're watching intelligence that doesn't map cleanly onto our categories, and that's just the beginning of how strange this gets. Beyond the coconut-carrying behavior documented in Indonesia, octopuses demonstrate problem-solving that extends into territory we typically reserve for vertebrates with far larger brains. Laboratory studies document sophisticated learning across multiple contexts. They open screw-cap jars readily, manipulate child-proof containers, navigate multi-step puzzles. They recognize individual humans, responding positively to some caregivers and negatively to others based entirely on prior interactions. This requires memory not just of events, but of specific identities associated with those events. One study demonstrated observational learning. When naive octopuses watched trained individuals solve novel problems, opening containers to access food, the observers solved identical problems significantly faster than control animals without observation opportunity. This suggests octopuses extract relevant information from watching others, an ability typically associated with social species. Except octopuses aren't social, they're solitary hunters who actively avoid each other outside mating. Then there's play behavior. Play is evolutionarily puzzling because it provides no immediate survival benefit. It consumes energy, requires time that could be spent foraging, sometimes increases predation risk. Yet play appears consistently in animals we recognize as intelligent: cetaceans, corvids, parrots, carnivores, primates. Octopuses in captivity have been observed repeatedly manipulating objects in ways that serve no apparent purpose beyond the manipulation itself. Bouncing balls, releasing objects into currents just to catch them again. This looks remarkably like curiosity-driven exploration. Multiple aquariums report octopuses escaping enclosures at night to hunt in neighboring tanks, then returning before morning. This suggests not just problem-solving ability, but spatial memory and what can only be described as planning. Multi-stage excursions requiring navigation, obstacle bypass, hunting execution, and route reversal. That's not instinct. That's strategy. Taken together, these behaviors provide compelling evidence for complex cognition in an animal whose brain architecture bears almost no resemblance to ours. Which brings us back to the central paradox. How did this intelligence evolve in a solitary animal? The social brain hypothesis has dominated thinking about intelligence evolution for decades. It argues that complex cognition emerged primarily to navigate social relationships, tracking alliances, predicting behavior, managing cooperation and deception. The hypothesis elegantly explains primate intelligence, dolphin intelligence, even corvid intelligence, all highly social species. But octopuses shatter this framework completely. They don't live in groups, they don't cooperate, they don't raise young. Females die shortly after eggs hatch, meaning there's zero parental investment, zero knowledge transfer between generations. Each octopus effectively invents octopus behavior from scratch using only genetic programming and individual learning. So what drove their intelligence? The answer appears to lie in ecological complexity rather than social complexity. Octopuses are soft-bodied predators in environments packed with both prey and predators. They're generalist hunters tackling diverse prey species, crabs requiring shell-cracking techniques, fish demanding speed and prediction, bivalves needing persistence. Each prey type requires different strategies, different approaches, different solutions. They inhabit structurally complex environments. Coral reefs, rocky coastlines, kelp forests. These habitats demand sophisticated spatial memory and three-dimensional navigation. They also contain numerous predators, sharks, eels, dolphins, against which a soft body provides zero protection. Survival requires evasion, concealment, rapid threat assessment. The ability to vanish isn't optional, it's mandatory. Their environment presented a vast array of problems. When the environment is sufficiently complex, intelligence emerges as a solution, even without social pressures. The octopus proves you don't need friends to get smart. You just need a world complicated enough to reward flexibility. Intelligence itself becomes a questionable term when we examine what it actually measures. We define it through our own cognitive architecture. We design tests privileging abilities humans possess: verbal reasoning, abstract symbolism, long-term planning with delayed gratification, complex social cooperation. When animals perform well on these metrics, we call them intelligent. When they don't, we often conclude they lack cognitive sophistication. The octopus reveals the profound limitations of this framework. Comparing neuron counts illustrates this clearly. Humans possess approximately 86 billion neurons. Octopuses have hundreds of millions, substantial but nowhere near human levels. Yet this comparison is almost meaningless because octopus neurons are distributed across a decentralized network optimized for problems humans have never encountered. Coordinating 8 semi-autonomous appendages, processing chemotactile information from roughly 2,000 independently operating suckers, generating coordinated color changes across thousands of chromatophores in milliseconds. Their cognitive architecture is adapted for their ecological niche, just as ours is adapted for ours. Neither is objectively superior. They're optimized for different problems. This has profound implications for how we think about intelligence beyond Earth. For decades, the search for extraterrestrial intelligence has largely assumed alien minds would resemble ours fundamentally. Social, technological, communicative through symbolic language. We've built detection strategies around finding radio signals, mathematical patterns, evidence of large-scale engineering. But if intelligence can evolve in such radically different forms on our own planet, in a lineage that diverged from us 600 million years ago, what might alien intelligence actually look like? Perhaps the universe contains minds more similar to octopuses than to humans, intelligent in ways we might not recognize as cognition at all. There's a concept in ethology called Umwelt, the perceptual world unique to each organism. A tick's Umwelt contains only 3 sensory cues: the smell of butyric acid from mammal skin, the temperature of blood, and the texture of hair. That's the entire universe as a tick experiences it. A dog's Umwelt is dominated by scent information we can barely conceptualize. Our Umwelt is shaped by language and symbolic thought. We experience reality through concepts, categories, narratives that structure perception before we're even conscious of it. An octopus's Umwelt is something we can barely imagine. A world experienced through distributed gustation, where every surface contact provides simultaneous taste and touch. Polarized light perception revealing patterns invisible to us. Autonomous limb sensation, where parts of your body gather information and make decisions without your awareness. And perhaps, strangest of all, a body that constantly mimics its surroundings at a muscular level, blurring the boundary between self and environment in ways that might fundamentally alter consciousness itself. That's not just different intelligence, that might be a different form of consciousness entirely. When an octopus changes color, is it thinking about camouflage the way we think about choosing clothing? Or is the mimicry something closer to reflex, bypassing what we'd recognize as conscious deliberation? The question assumes consciousness works the same way across species. It probably doesn't. We've only begun mapping octopus neurobiology in the last few decades. The discoveries keep getting stranger. Individual suckers can taste and make feeding decisions independently. Arms severed in experiments continue exhibiting goal-directed behavior. The skin responds to light without brain involvement. These aren't signs of a defective system. They're signs of a system built on completely different principles. Cephalopod intelligence evolved roughly 300 million years after our lineages diverged. That's an enormous span of independent evolution, long enough for entirely different solutions to emerge for the same fundamental problems. How to navigate complex environments, how to find food, how to avoid becoming food, how to reproduce successfully. Evolution doesn't converge on single solutions. It explores possibility space. And the octopus represents a fundamentally different exploration than anything else alive today. A decentralized network rather than centralized control, chemical sensation rather than primarily visual, autonomous body parts rather than unified command structure, camouflage as a primary survival strategy rather than size, speed, or social cooperation. Every assumption we make about intelligence carries hidden biases. We assume memory requires hippocampal structures because ours does. We assume learning requires consolidation during sleep because ours does. We assume social complexity drives cognitive evolution because it did for us. The octopus violates every assumption while still exhibiting sophisticated, flexible behavior. This matters beyond academic curiosity. If we ever detect signs of life elsewhere in the universe, we'll need frameworks for recognizing intelligence that don't assume it looks like ours. The octopus provides the clearest proof that intelligence can emerge from completely different evolutionary pressures, operate through completely different neural architectures, and produce sophisticated adaptive behavior without resembling human cognition in any fundamental way. Perhaps intelligent life exists throughout the cosmos, but operates on principles so foreign we don't recognize it as intelligence at all. Communication through methods other than electromagnetic radiation. Cognition distributed across systems rather than localized in brains. Timescales so different from ours that meaningful interaction becomes impossible. The octopus suggests intelligence is substrate-independent. It doesn't require a particular type of nervous system, a particular body plan, or a particular evolutionary history. It requires only complex problems and sufficient evolutionary time to develop solutions. So did the octopus break evolution's rules? No. It revealed our understanding of those rules was incomplete. We wrote the rules based on vertebrate evolution, primate social structures, a sample size embarrassingly small given life's diversity. The octopus forces us to rewrite those rules. Intelligence doesn't require centralized processing. It doesn't require social groups. It doesn't require parental care or cultural transmission. It doesn't even require a lifespan longer than a few years. It requires only an environment complex enough to reward flexibility, variation in neural architecture to explore different solutions, and selection pressure favoring individuals who solve problems more effectively. Given those ingredients, intelligence emerges. Not once, but repeatedly, in forms we're only beginning to recognize. No, The octopus will never build cities or develop technology. Its lifespan is too short, its lifestyle too solitary, its body plan poorly suited for tool manufacture. But intelligence was never about technology. That's a human bias. Intelligence is about solving the problems your environment presents. And by that measure, the octopus succeeded spectacularly. It became one of the most effective predators in one of the most competitive ecosystems on the planet. Despite lacking shells, lacking size, lacking the social structures we assumed were necessary, every octopus that carries coconut shells across the ocean floor, every individual that learns to open jars, every animal that adjusts its camouflage to match substrates it's never encountered before, proves intelligence is far stranger and far more diverse than we imagined. We're not alone in possessing sophisticated cognition. We're just alone in assuming our version is the only one that counts. The octopus doesn't care about our definitions. It solves problems, survives, reproduces, and in doing so, quietly demonstrates that the universe of possible minds is vastly larger than the tiny corner we occupy. There's something humbling about watching an octopus vanish into coral, knowing it solved a problem our entire lineage never had to face. We built our intelligence around language, around shared knowledge, around raising young that carry forward what we learned. The octopus built theirs around something else entirely, around arms that think independently, around skin that tastes the world, around a lifespan so brief there's no time for anything except raw, immediate problem solving. And maybe that's the point. Intelligence isn't one thing. It's whatever works for the problems you face. For us, that meant social cooperation and symbolic thought. For the octopus, it meant distributed cognition and adaptive camouflage. Neither is more valid. They're just different paths through the same brutal landscape of survival. When we look for intelligence elsewhere in the universe, we'll probably look for versions of ourselves. Radios, mathematics, megastructures. But if 600 million years of separate evolution on the same planet produce something as alien as the octopus, what might truly alien intelligence look like? Maybe we're surrounded by minds we can't recognize because we're still assuming intelligence has to look like us. The octopus already proved it doesn't. We share a planet with an intelligence that thinks with its arms, sees with its skin, and rebuilds itself every time it needs to hide. That's not a curiosity. That's a fundamental challenge to everything we thought we knew about minds. And if we're lucky, it's preparing us to recognize intelligence when it looks nothing like what we expected.